Welcome tonight. Good evening. You should be able to hear me, and the chat should show up in the chat box off to the side. And I'm just getting up my document here. And there we go. Looks like we have some people on board here. So you should be able to see the chat link over on the side. If you can't, you can text me at 414-899-8269. And that should work out pretty well. I'm going to share the study guide with you. So you should be able to see that. And so what I'm going to do tonight is similar to what we did last night, and that is I'm going to go through the study guide, tell you a little bit about the things that I think are important, and answer any questions that you might have as we go along here. And I think the Q&A, you should be able to see the Q&A over to the side as well. And if not, I think there's a Q&A button over on your left side, the fourth item down. If you don't see it over there, you can push that, and you should be able to either ask questions, and I'll try and address those. So let's go ahead and get started. I'm going to spend a few minutes going through each of the items, what I think is important, what you should be taking a look at, and then go back and talk about some of the items in detail. The overall format of the test will be some multiple choice questions, some short answer questions, and then 3 longer answer questions worth about 10 points each that will ask you to diagram some answers. So the first half of this class, the first half of the semester, has been devoted to thinking about sort of the front end of the development process. And remember that there are sort of 2 main parts to software engineering. There is the software development activities, such as requirements analysis, domain modeling, design, implementation, testing. And then there are managerial processes, such as project management, configuration management, that we're going to be talking about later in the semester. So you want to go back and take a look at what the software development process activities are and what those component activities are. One of the things that I've stressed throughout this is the notion of the 4+1 view of architecture for software. The reason I want you thinking about that and familiar with it is because software development projects are complex, there are a number of different stakeholders with different viewpoints onto the system, what's important to them. So far, we've been thinking primarily about the logical model of the system. And you'll recall that's sort of that upper left-hand corner in the diagram. And the reason that we focus on that part first is we're thinking about creating models of the system, thinking about what we need to design, and then we'll be thinking about the development process itself and how we deploy it later on in the semester. And in order to get that going, I'm just going to scroll this up a little bit here. In order to get that going, we started to think about tools that we use for modeling the systems, because as I've mentioned frequently, we're thinking about larger systems and we create the models to help us understand the complexity of it. And one of the first ones we looked at was a way of capturing requirements through the use case model. And one of the important things to know here is that the diagrams, the pictures that we see, are a representation of the models that we're creating. Use case diagram shows us pictures of actors, the use cases, and the system boundary, and that those are all elements of the use case model. The actor, which use cases there are, what their relationships are, and the system boundary. Those help us determine the functional requirements of the system, who we're interacting with on the outside, in other words, what our dependencies are. And then the individual use cases are really classes of scenarios, as we've talked about a number of times. So the class diagrams allow us to start to model the abstractions in the system, their relationships, and multiplicities. Object diagrams, on the other hand, show us specific instances of classes, how they're linked at some moment in time, and how they interact with each other in order to support scenarios. Now, not surprisingly, class diagrams can exist at very high levels of abstraction or lower levels of abstraction and more, design level type levels of abstraction. And so when we start to do requirements modeling, which we'll talk about in a moment, we're going to be thinking at the higher levels. Now, throughout this, we're presuming that we're doing iterative development, and what we're doing in that iteration, the different steps within the iteration, and how we plan out what features we're going to implement at each iteration. And the idea is that rather than having long cycles of requirements, analysis, design, testing, we're doing these over and over in small chunks and allowing us to do our invention on an iterative basis so that if we make a mistake, we can back up a little bit. So what I'd like you to know about iterative development are what those steps are: the planning, the planning, design, the implementation, test, and review, and that we're going to go over through a number of iterations. Some of those iterations are candidates for release, and in our case, we're doing 4 iterations to get to our final release. Now, as we start to look at systems, whether we're doing agile development or more traditional, longer cycle development, we do have to look at the required behavior of the system, and frequently we will model it using use case models to understand what actors there are on the system, what use cases it supports, and what that system boundary is. What are we responsible for? What are we not responsible? So we've talked about some ideas for how we support the identification of actors in the system, how we identify the abstractions in the system, and we start out by going through scenarios. And scenarios are typically initiated by an actor and show the sequence of events between the actor or actors, between the actor and the system, to deliver some element of value. And those are usually capturing functional requirements in the system. Now, we make a distinction between functional and non-functional requirements in the system, where functional requirements are things the system does in response to some event and delivers some value. Non-functional requirements are typically qualities that we attach to that response. In other words, how we do that response. Now, there are, on occasion, there are very narrow differences between those, but I'm going to try and keep them pretty separate. Functional behavior, what the system does. Non-functional requirements are typically constraints placed on that behavior. In other words, describing how that behavior takes place. An example might be for our ATM. We come up and the functional requirement is that if I present myself and identify and authorize myself, I can select the function withdraw cash and get my $20 out of my account and get a receipt. The non-functional requirement might be that I can support up to 20,000 users simultaneously. Notice that that doesn't change the functional behavior of the system. It simply allows me to place a constraint on how that behavior is delivered. It's a subtle distinction, but it's important in that the users tend to think about what the system does for me, and the system architects then go in and see if they can meet the requirements for how quickly, how reliably the system operates, or how easy it is to modify it, or how secure the system is. So those tend to be non-functional requirements. So as we're going through the scenarios that I was talking about here in the requirements gathering, as we go through scenarios, we're identifying actors and abstractions in the domain and how they're related. And we start to think about the abstractions that exist, and we start to build up our domain model. And the use cases are really classes of scenarios. They're groups of scenarios that say, well, these are all scenarios that have to do with withdrawal. These are scenarios that are really part of deposits. These are scenarios about making transfers. And they typically are different scenarios based on conditional behavior within it. And we saw some examples in, say, the monopoly example. Just going to scroll up a little bit here. On that second page, I forgot to mention some issues of performance and scalability are two examples of non-functional requirements. How fast something happens. You always want your non-functional requirements to be measurable. If you say that something should be fast, you can't just say as fast as possible. You have to say that the response after putting the card in the ATM must be less than 1 second. Something that can be measured in terms of that quality. So under domain model, when we think about the domain models in systems, we're starting to create a glossary of what's important in the system. And I'm going to get to that question in just a moment there. We're starting to create a glossary of the abstractions that exist in the system and their relationships. There was a question on non-functional requirements. It says, since it specifies a range for the speed value, for example, in the aircraft must report its speed upon request as a range of 0 to 1,000. That would be a non-functional requirement. So it says, so you would think of the functional requirement is the aircraft must be able to report its speed. And we're saying that that exists in a range. So typically when we would do that test for it, we'd say, okay, the test plan for aircraft reporting speeds, and we'd make sure that aircraft, for example, don't report speeds of less than 0. That what happens if an aircraft is actually going more than 1,000, for example. So that would place constraints, and typically a lot of those non-functional requirements also help us with boundary value analysis. Trevor's asking, would having to report its speed in the first place then be a functional requirement? And yes, it would be. So one of the functional requirements would be that an aircraft, when a aircraft controller requests the speed, that it respond with a speed. And that would be the functional requirement. And that's what I was saying before, is sometimes there's a very, you get into a narrow distinction between functional and non-functional requirements. Usually when we're testing functional requirements, we're looking for behavior in the system, and the non-functional are typically going to be constraints on that. In the test, it will be very clear whether it's a functional or non-functional requirement. In our domain models, when I ask you to do those, what we're doing is we're looking for those abstractions and their associations, such as composition, for example. We're also looking for relationships in terms of multiplicity. How many, we looked at some examples where we said an airspace can have 0 to many aircraft in it. Not only does that tell us about the domain itself, but it forces us to ask questions about the domain. If we don't know what those numbers are, we should probably go back to the user and say, you know, you said it has some aircraft in it. I can't attach any numbers here. Can you give me an idea of how big this is? Is it like 2? Is it like 1,000? Is it 1,000,000? And the user or the end user would say, gee, I don't know. I've never thought about it. Or they'd say, oh, well, no, we would never have more than about 200 aircraft in the area. And so you can start to at least attach notions of what's the right size for that. Later on, when we go to do our design, when we start to drill down on that, we'll go, this number isn't so huge. So from a performance perspective, we may elect to do an implementation that is relatively inexpensive and fast. But if it's a huge number, then, oh, we may have to make other accommodations for that in our design. So when I've asked you to do domain models, typically they're not very large. The number of abstractions in the system isn't huge, because remember, you're focusing on the domain model, not on your design model. And that's an important distinction, because very often what happens is people start thinking about how they're going to design it, and they start doing design in their requirements world. And it gets a little muddy, because all of a sudden they're dragging in lists, or they're deciding, oh yeah, I'm going to put it in this component over on this server. We don't want to do that. We're trying to focus on the problem space itself, not on the solution space. Then we skipped over design a little bit, but we did talk about one important notion, because we're going to be coming back to design. When we talked about design, we talked about how we start to cast our domain model into a solution space by thinking about what objects we have to build in order to support that domain. And we saw an important one, which was that compiler example, and that's worth going back and taking a look at, because it's a very good example of the interface pattern, which is I have one class that acts as the interface to a number of other classes that support my behavior. And you're going to see that over and over, because really, when we saw that compiler example where the interface said, well, I compile some file, what we are really saying is this subsystem provides a service for you, which is to compile a source code file into executable code or into interpretable code. And I have a number of classes of objects inside me that actually do the work, but they hide behind me. They're behind this facade, is one name for this pattern, or this interface pattern. And that allows me to start thinking about components before I actually have to build them. I can say, oh, this component is responsible for compiling. And so the interface is, here, take this file, compile it, and return a fully compiled result. And then I'll worry about how to implement it. So we start progressively pushing down these implementations. Now, from a testing perspective, and then we're going to come back to some more design stuff here in a moment. I brought up the testing stuff early on. You know, I sort of promoted it, even though it was later on in the book, because I really like to focus on thinking about how I'm going to test something. Because I really like doing demos of software, and in order to demo software, a good demonstration is really taking all of the system level use cases and showing them off to somebody as a story. Well, if I'm going to do that, I should have planned on how I'm going to test each of those so that that demonstration goes perfectly. And so for my testing, I have two important distinctions here. There's test plans and test cases. A test plan tells me about how I'm going to test something. What do I have to have with me? What features is it that I'm testing? What's the scope of that? Is it like all of the transactions on my ATM, or is it just the withdrawals? And if it's just the withdrawals, what resources do I need? Do I need an ATM simulator? Do I need a bunch of test data with some test accounts at known values? And then it tells me what test cases I'm going to execute. So the test cases are the very detailed situations where I say, this is the test I'm going to run, and I'm going to have an expected value that I get out and an actual value. And the difference between those is my error. When we talk about what errors are in the system, it's the difference between what I expected to happen and what did happen for that test case. So for lower level components, the test cases tend to be pretty simple. I'm testing each of the methods, and within those methods, I'm expecting to cover all the statements in it, including the different branches. And it's worth your while to go back and look at that basis path calculation. And it sounds a little wonkish, it sounds a little formal, but what it's doing is giving you an idea of how complex your method is. If you have a bunch of branches going on and a bunch of compound conditionals, which everybody loves to write, it's going to increase the size of your flow graph, and all of a sudden you have a lot more test cases. You'll remember in that simple test case that we saw with that, I don't know, what was that, 15 lines of code or so? We saw that it exploded into quite a few different test cases just because you had all those different combinations of inbound parameters. So methods that have a large number of parameters and methods that have lots of conditional branching in them are going to cause you headaches when it comes to branching and statement coverage within them. So branch coverage says, I want to make sure I take all the possible branches in the system. Statement coverage is, am I actually hitting all the statements? Now, modern compilers are pretty good at saying, hey, you know, this statement can never be reached. You've probably seen that in a compilation here and there. But for the most part, you want to make sure you've hit all the statements. Method coverage refers to the fact, have I actually tested all of the methods that are available in a particular class? Now, we tend to automate most of the lower level unit functions because we want to do those every time we make a change. We want to go back and run all the tests to make sure they all still work. As I start to get higher up, I'm doing integration level testing. And with the integration level testing, I'm saying, let's take several objects, put them together, and test them in a scenario to make sure it supports that scenario. All of that comes under white box testing because I've needed to know exactly how this thing is built. Black box testing, of course, is the process of making sure that you understand that for all of the inputs that you intend to provide, you get the expected output without knowing what's going on inside. Now, I have boundary value analysis and system level use cases under this. Boundary value analysis is typically where you're saying, I want to test things at various inflection points in the range of input data. So, for example, when we were testing our ATM, we thought of, well, what happens if I withdraw the exact amount of money that's in the account? What happens if I try and withdraw $0 out of an account? What happens if there's $80 in the account and I do 4 $20 withdrawals? That would be important. What about trying to withdraw $25 when it only has $20 bills to dispense? So we're trying to come up with the different combinations that would allow us to test the different boundary values, the different boundaries of test conditions. And we saw that using our domain model, that helps us start to generate some of those boundary values, maximums, minimums, inflection points, etc. So we spent quite a bit of time looking at that testing and making sure that at a system level, we could test to make sure that all of our use cases are covered. So basically, for each use case, we should be testing all of the scenarios that we believe are representative of those use cases. So a use case for the ATM was that I'm going to go up, present my card, withdraw $20, and get my receipt printed. A second system level test would be, I'm going to present my card and put in the wrong PIN number. Another system level use case would be, I've authorized the PIN, but I've tried to withdraw more money than I have. Those are all reasonable system level use cases. In other words, the actor is initiating the scenario, and I carry through to the end of that scenario. So if you ask a user to perform the tests that they should test, that they should execute in order to accept the test, the system, sorry, let's back up. The user can execute a set of tests that they view as, if these tests are passed, then I will accept the system. Those are acceptance level tests. And those are usually dictated by the end user or the customer. As the designer and the engineer responsible for the system, I may do a number of system level tests that outnumber the ones the customer does. I'm trying to do as much white box testing as possible to make sure that I've covered all of my bases. There's a question here. It says, do testers in black box testing know the interface of the class being tested? Yes, they do. And that's really the distinction here, is they say, I know exactly what the interface is, and I know what I need to test against. And I know what the output should be, but I don't know how it's done on the inside. Okay, so that's the versus white box testing, which is, hey, I know that if I provide 0 here, even though that's not something the customer is doing, I can break the system by supplying a -1 for the amount. And so if you have internal knowledge of where the sensitive parts in that software are, the soft underbelly of it, if you will, then you are doing more extensive testing than that customer may do. Black box testing says, here's how I intend to use it. For example, if somebody gives me a component for drawing boxes, drawing two-dimensional figures on the screen, I may test it to say, well, I intend to draw boxes of this size, and I'm going to draw them using integers with integer dimensions. I'm going to run my series of tests, and as long as it draws all the boxes I expect, then it passes my test. So the white box testing, on the other hand, says, even though you may never hit these different branches, I'm going to cover all the branches just in case. Then finally, on Tuesday, we sort of initiated our discussion on more detailed design by talking about the fact that there are a lot of recurring patterns in the solution space especially. And we said that patterns exist at various levels. Code level, like looping, at the design level, at requirements level, and at domain level. And I'll get to the question about question 6 in just a moment. So we started to talk about design patterns, and one of the things that's important to know is that a pattern is a solution in a context. It's a solution to a problem in a context. And the reason I put that up on the screen and said, you know, this is important to know is the pattern is not the solution itself as a, it's only when I take into account the context in which I am and I sort of fill in the missing blanks that I actually have the total solution. And so that pattern is a solution to a problem in a context. So we looked at two other patterns besides the interface pattern here, and that was the publish, subscribe, or the observer pattern. And that was how I could deal with objects that say, hey, when I change state, I want somebody else to know about it. But I don't really know who they are. I just know that I have a list of interested parties. It's kind of like a Twitter or Facebook follow, which is when something happens on my timeline, I'm just going to tell this whole list. I don't even know who they are. And I'm going to notify them that I've changed, and they can then elect to come back and update themselves. A great example is a Facebook follow. you'll get a little notification in your news that says, say, somebody just posted a picture of John. And you then turn around because you got a notification. Your response is to go back to that timeline and grab the picture and take a look at it. You made a request of that other object, that person's timeline, and said, hey, show me the picture. But notice that the subscriber, the original publisher said, I don't really know who's in my follow list. I just let everybody know that I've changed. And we saw this very loose coupling between the publisher and the observer. The publisher and the subscriber, or the observer and the observed. And the idea was to keep it very loosely coupled so that anybody could subscribe and get a notification. And we see that pattern all over the place, especially in distributed systems. Now, one of the comments I just made there was, boy, that's very loosely coupled. And that takes us back to the concept of cohesion and coupling. And I don't have it actually written on the sheet here. I think I did. No, I didn't. The notion of cohesion and coupling is important because we're always trying to minimize coupling, maximize cohesion. But when we try and overdo it on one side or the other, we tend to drive the other up. So if we try to be overzealous in our decrease in coupling, then we tend to drive up. We destroy the cohesion in the other objects. We put too much in them. So we're trying to have an object be nice and cohesive so it's easy to maintain. And we're also trying to have a system with relatively low coupling so that it's easy to modify and easy to test. Because when we were talking about testing that one day, we said, boy, in order to develop a scaffold, in other words, a setup of objects that we are going to test, we said, well, if I'm going to test this object, I need these 4 other objects in order to test it, because there's a lot of coupling. Suddenly the tests get a lot more complicated because each of those those objects that it depends on also have state. So suddenly things get very complicated. So I'm always trying to minimize my coupling. So remember your definitions of cohesion and coupling there. Somebody asked about question 1 in quiz 6, and I just need to jump back and take a quick look at that. Because sometimes your mind fails you. The question being about black box testing. And it said black box testing focuses on, and we had 4 options: the structure of the component under review. No, it doesn't do that. In fact, we're looking at just the interface to it. The second possible answer was B, measuring a result from a given input. Yep, when we make an input, we go back and measure the output. This third possible answer, C, using random input data to force errors. One could say that, but you're more interested in understanding what the result is from a given input. D is testing a known interface with an unknown implementation. The testing itself is actually this process of measuring a result from a given input. And so D would be kind of an answer to that, but the best answer is B. Now, when you test the interface, you do that by measuring the results from given inputs. So that's going to be the hair splitting that goes on there. And I can understand why somebody might have thought that D was a reasonable answer. Just gotta go back to where I was here. There we are. Let's see, what else are we missing here? I think that's about it. So the first half of our semester, we're just a little bit shy of halfway through, just because of the way the break falls. We've really focused on sort of this soft front end, where we're thinking about what we need to build and how we're going to test it. And the rest of the semester, starting when we get back, is we're going to start to think about how we actually build these systems. What design patterns do we use? How do I do refactoring? What's the best way to break the system into components? How can I manage threads? How can I optimize the code at lower levels? How can I make sure the system is maintainable? So we're going to get into a lot more architectural issues that go on. We're also going to do some work with HTML and CSS so that we can improve our particular project that we're working on. So the lab that you did this week was sort of an introduction to how we think about systems being distributed. And what you were really doing is you were sending a message between two different processes. And a message is simply an event that can be interpreted when it arrives on the other side. But so we're starting to, that lab was the first of our more difficult implementations, thinking about how we're able to distribute our system to achieve some of our results. So I think we've hit on all the important things. If you've done the reading, as I said before, you should be in very good shape, because that covers lots of stuff. In terms of the overview, just scribble on your notes there, cohesion and coupling. Go back, take a quick look at cohesion and coupling there. You should be able to do basic UML modeling, including the appropriate or standard UML notation for a class, which is the box, or associations, basic multiplicity, meaning how many on each end, a little bit of inheritance, the basic generalization, specialization. You should be able to understand the difference between an object and a class in a diagram. The class diagram is showing sort of structural, logical relationships between the abstractions. Object diagrams are showing specific instances. And then pretty important was the notion of the use case models and the identification of the requirements, and then being able to make the distinction between test plans and test cases, very important. And then take a look at that flow graph example. Again, the reason I want you to look at that is not because I want you to drill down to that level of formality, but it's forcing you to think about, wow, if I have really complicated cyclomatic numbers for a method, maybe I should go back and start to think about better coding practices that make it more testable. Because in the end, as I mentioned a number of times, you want to think about, how can I design this so that not only it works, but it can be tested. And then the inner subscribe or observer pattern and the memento pattern, which you should know. That's about here, can you elaborate on UML? Not important. That said, the distinction is that an include, you can think of an include as saying, I've identified a part of the use case that I see in lots of different places, and I'm going to make that like a little sub use case. The notion of extends is more along the lines of inheritance, which said this use case is like this one, only a little bit more complicated. And just like in inheritance, I can model all inheritance as composition. You may have heard that in your lower level programming classes. But extends is a notion of use case modeling that says, this is like this use case, only I override or I change some of the behavior in it to get a more specialized version. But for this test, you don't need to know that distinction at this point. But I will follow up on that in class sometime. Let's see, there was another one. I think that was it, actually. Just gonna take a quick look over here. That should be about it. I think if you've done that, practice a little bit just doing some quick use case models and domain models, you should be good. Oh, be sure you bring a pencil or something to write with. You can bring a pen, of course. It's just pencil is a little bit less of a commitment and does allow you to change your mind. Oh, there was one other question here. Can you give an example of communication diagrams? We looked at one for, if you go back and look in your notes on scenarios from requirements, we looked at, I'm trying to remember exactly what day it was. I think it was week 5. No, maybe week 4. We took a look at how aircraft are handed off. And so you can think of a communication diagram as a timeline for objects. I don't have a good way of quickly drawing those up right here. I'll give you a little hint. You don't need to know that for the test. So that's a benefit of hanging on here. There's 19 of you that know that. So a communication diagram or an interaction diagram allows me to show the specific interaction between two objects, not two classes, two objects. And what that means is that two instances of some classes, I am going to show over time the messages that transpire between those two. And while we're talking, I'm going to see if I can create a little picture of that to show. I'm going to open up my Gliffy diagram here. Give me 2 seconds. The interaction diagrams, as we saw in our examples, are a way to think about scenarios. And when we give examples of scenarios, we're typically describing the interactions between them. And I'm going to, in fact, show you the example from Lab 7 here. So I'm going to share that now. If I do this right, it should all work out. Lab 7. Okay, so you should be able to see that. So the interaction diagram that we have here is, if you look at the top 4 objects here, the one that says main, client, site, HTTP URL connection, and HTTP handler, those are objects at the top. And there's 2 parts to them. There's the object name, main, and its type, client. Whereas over here, if you look at HTTP handler, I don't know the name of it. That was sort of created on the fly, and the handle to it was passed off to another object. But it is of type HTTP handler. Those vertical boxes that go down are simply the activation of the object, the time it's alive. And then we see the messages that are passing between them. And what this is this is almost, if you described somebody going up to somebody at a bank, you might have the client and the bank teller. You say good morning, and they say good morning, and then they say, I'd like to take some money out of my account. and they say, can I see some ID? And they say, yes, I'd like $20 out of my checking account. And they give it to them and they're done. So it's this interaction between two objects. And so this is the way we typically think about a scenario, and we start to describe it, and we start to flesh it out. Initially, you might just say client, connection, handler, and server, and then you start to improve upon that. And so by looking at these interactions back and forth, you're really describing two different things going on. First of all, who the participants are, what messages go between them, and sort of the state change that happens over time. Because obviously, as each of those messages is passed between the objects, that potentially the state of those objects are changing. And notice that I'm using the word object here. These are not classes, right? Instead, I'm talking about specific instances within this. So if I were to go back to that for a moment and go to my class diagram. Let's see, it's not on here. If I look at the chronotimer domain model, notice that these are all classes. And I think you should be able to see that. Let me just make sure you can see that one. Yes. Here you're seeing the classes and their composition, and that's describing classes of objects. So it says, if you had a chronotimer, you would also have a display and a keypad and a printer and a system clock and a channel, but it doesn't show me a specific instance of those. Now, you know, that's kind of splitting hairs for some people, but it is important to be able to make that distinction between those. Let's see. Come back and share my I think that's about it. Well, good luck. Bring your pencil tomorrow, and you'll have plenty of time to do it. It's designed to take about 40 minutes to do, or 35 minutes to do. That way we'll be out of the room before our very eager history of social sciences class comes in, but history of sociology class comes in behind us. Make sure you bring something to write with, and we'll see you at 10 o'clock tomorrow. If you have other questions, feel free to email me, but I think we've gone through everything that you need to know tonight. Have a pleasant evening, and we'll see you then.